Hi everyone. Can you hear me? Okay. So hi everyone and welcome to my talk about reverse engineering Denuvo and Hogwarts legacy. First, a few words about me. Who am I? My name is Maurice Heumann and I'm a cybersecurity engineer working at Thales. And I used to mod Call of Duty games back in the day, so maybe you know me from mods like Boy or XLabs. And you can also follow me on Twitter if you want. The agenda today will be, first we'll try to understand Denuvo, what it is. Then we'll try to analyze it and to find out how it works. And then we'll try to patch it or to bypass it. And at the end there will be a bit of a performance reasoning to have a look at the performance of the game. So first, let's start by understanding Denuvo. Maybe some of you already know what Denuvo is. For those of you who don't know, it's an anti-tamper solution developed by Denuvo, and the main purpose is essentially to protect games from being copied. For example, Hogwarts Legacy, so that you can't pirate the game. And it's essentially not really a DRM itself, but rather it's a solution that protects existing DRM solutions. For example, you have the Steam DRM layer, the Steam licensing system that Hogwarts Legacy uses, and Denuvo prevents you from removing the Steam licensing solution, so you need to own a license for that game. And in my opinion, it's one of the strongest protections there are to this date. So how does Denuvo work? You have the game, and on the other side you have the Denuvo server. At the beginning, the game will try to generate a hardware fingerprint, which essentially consists of your computer name, your username, and some other identifiers that we'll see later. Once Denuvo has done that, it will generate a so-called Steam ticket. A Steam ticket which is essentially proof of game ownership, so that once these two things are generated, they're sent to the Denuvo server, and the server can then check that you really own the game by validating this Steam ticket. So it checks that you own the game, then will then probably communicate to the Steam servers, check that you own the game. And if you really do, it will generate a Denuvo token that specifically matches your fingerprint. And at the end, the game is able to run using this Denuvo token. So that's the startup process of Denuvo. So you might ask yourself, what's this fingerprint? And it's essentially a collection of features that uniquely identify your PC. So it could be your computer name, your username, some other identifiers that identify your CPU, maybe some operating system identifiers. There is a whole list of features that Denuvo uses, and it varies for each game. So not every Denuvo protected game uses the same features to identify your PC, to identify you. The Denuvo token itself is I guess it's an encrypted or encoded XML file. I tried to decode it and it looks like this. I hope you can read it. It starts with some app ID. In my case, it was the Steam app ID of Hogwarts Legacy. And then it contains some user ID of the user who owns the game, in case that's my Steam ID. And at the end, there's some encoded game token data. I didn't try to look what that is. It looks a bit like base64, but it's not. So I don't know what that is. But the important point is that this data belongs to your fingerprint, so it specifically matches the fingerprint that was generated from your PC. And then once the Denuvo server has sent the token back, it is being stored on disk. And that means that online connectivity is only required for the first launch or if your fingerprint changes. So normally the Denuvo game will not require any internet connection except for the first start. So what is this Denuvo token used for? And essentially Denuvo has two phases. The one I showed before with this ping pong process is what I call the startup phase. And essentially it's the fingerprint collection process and then this token generation. And once you have this token, there's the runtime phase when the game runs and you play the game. And this runtime phase only works with a valid token. And the reason is that Denuvo continuously validates your PC during runtime. Don't worry, it happens outside the render loop. But the essence is that your PC is being validated. And I don't know exactly how it works because I didn't reverse engineer that in detail. But I assume that the game reads some of those fingerprint features, for example, your computer name, and then it uses that to encrypt data of the game. So data at runtime is being encrypted using, for example, your computer name. And then this token contains the necessary information to decrypt that piece of data again. And that means that if the token doesn't match, for example, your computer name doesn't match what's stored in the token, then the game will probably crash. So that means that your PC needs to match this token. And what makes Denuvo so strong is that they have an individual protection for each game. First, these fingerprint features, they seem to vary for each game, maybe even each game version. So I checked different Hogwarts Legacy versions, and it was different. And the most important point, I think, is that there is a super strong integration into the game. So it's very hard, if you look at, for example, the game binary, it's very hard to differentiate between original game code and then the code that Denuvo inserted to protect it. And the integration is so strong that you can't really distinguish between the two parts. And by doing that, Denuvo has the option to perform this runtime validation at thousands of different places, which essentially makes a generic crack pretty much impossible. So if you want to crack a Denuvo game, you have to look at it, each game individually, and design a crack specifically for this specific game version. So now you might still wonder, how is it possible to bypass Denuvo? And in my opinion, there are two possibilities to do that. You can try to remove Denuvo from the game, so try to separate the Denuvo protection from the game and just remove it. In my opinion, that's completely insane. I think there are people who did that, but on older Denuvo versions, but on the latest version, it's just an insane task because you can't separate the two pieces from another. And the other way to do it is you essentially try to patch the fingerprint. So if the game reads, for example, your computer name, you try to patch that and feed a different value. For example, the value of a PC that has a valid Denuvo token. And this is what I did. So the goal is to replay the fingerprint features of a different PC and then hard code the token that was generated for this other PC and reuse it on my machine. This is what I did. And to do that, I first need to find all the features that Denuvo uses to identify this PC, and at the end I need to patch them. But first, let's try to focus on this analysis part, especially on how we can find those fingerprint features. And once I looked at Denuvo, I also thought to myself, how can I do that? How can I find out what Denuvo does and how it identifies your PC? And what I came up with is that Denuvo somehow must communicate with your operating system. It needs to communicate with your hardware, with the file system, anything to gather information about your PC, to gather identifiers. And I think there are only three main ways of communication that a Windows process can do. The first one is API calls. So you can, for example, call the Windows API and get the Windows username. You can read memory inside your process that might contain information about your PC. Or Denuvo could use, for example, special CPU instructions that reveal certain things about you, about your CPU. For example, there's the CPU ID instruction, or Denuvo could perform syscalls, or there are other ways to identify a PC using instructions. So we somehow need a way to analyze all these three types of communication. And for that, I have something that's called Sogen, which is a Windows user space emulator that I have developed. And maybe some of you remember I was already here last year and I presented a Windows user space emulator. And meanwhile, it got a name, so it's now called Sogen. And the idea behind that is that we let the game, Hogwarts Legacy, run inside this emulator, which has an emulated CPU, emulated memory, and by doing exactly that, we have the option to completely instrument the game. So we can look at each instruction that's being executed, because as we emulate the CPU, we can also look at the instruction that's being executed. And as we emulate the memory, we can also analyze any kind of memory interaction. And by using this emulation approach, we have super strong instrumentation capabilities. And what Sogen does for me, for us, is that it tries to log anything that it considers suspicious. So it will look at any instruction, any memory access, any API call. It will analyze anything, and it will print it out in a console for us to look at it. And I hope that this works, because I will try to do a demo. You can check it out on sogen.dev if you want, but I hope it's readable. And this is the website. You can also find my talk from last year at the bottom if you're interested on the technical details on how it works. But I also managed to compile this emulator to WebAssembly, so it should run in the browser, I hope. So if we click on Start, it should try to load a file system that mimics Windows. So it's essentially some kind of mini Windows emulator inside your browser. And you will also see some Windows DLLs in there. And what we can do now, we can add a file, this Hogwarts legacy binary, and we can just let it run. I hope everything is readable. Let me check the settings. That looks good. So what's happening now is that inside my browser, this Hogwarts legacy Windows binary is being executed within the emulator. And on the right, you can, for example, see the amount of instructions that are executed. You can see how much memory the process consumes. Yeah, I guess that's readable. And the amount of active threads. And after some time, we should see some logs. And the first thing we see is that Hogwarts legacy, or to be precise, this Denuvo startup sequence, seems to be executing virtual protect. And we don't care about that. We can see some import read access. Let's also skip about that. We can see that it tries to access somehow the command line. So there seems to be a way to configure Denuvo via your command line, but I don't know how. I didn't look into that. And once we skip over this, we can also see that it tries to read environment variables. That's maybe not super readable, but it's also some Denuvo debug stuff. So you can apparently configure Denuvo to do some debugging, but we don't care about that. And this is now where the interesting part starts. So we can see that Hogwarts Legacy executes a virtual alloc function, and it does that by allocating memory that is readable, writable, and executable. And what I think is usually, at least other Denuvo protected games use that to like outsource protected code into this executable section and execute it from there to make reverse engineering harder. But it turns out that this is not used in Hogwarts Legacy. So after that, we can see that the emulator prints that there was a import read access. And what this means is that Denuvo reads from the import table of the game, so the table that contains all the imported API functions, and Denuvo tries to access them. And I think what it does here, it takes, for example, this one, the API call setThreadAffinityMask. It uses the address that is stored in this import table, and then it compares it to, for example, another import from the same library. And by essentially subtracting these two addresses, you get the distance of those two functions within, for example, kernel 32 DLL. And if you upgrade your PC, then chances are high that kernel 32 DLL also changes. And that means that the distance of those two functions will also change because the DLL likely got recompiled. So by measuring the distance between two functions of the same library, Denuvo can essentially see that your PC has not changed. And they seem to use that as a fingerprint feature. I'm not sure if they're exactly using the distance or something else, but by accessing the import table, Denuvo starts to gain insight about your PC and tries to form this fingerprint. So this is the first thing that happens. And once we scroll down, we can see the first interesting thing that happens. We can see that Denuvo executes a CPU ID instruction. And for those of you who don't know what it does, it's an instruction that Intel provides to deliver information about your process, for example, special capabilities, if there's AVX instruction support or things like that. And using the leaf, that's what it's called, you can get the feature set that your CPU supports. And Denuvo seems to at least use this returned value as part of the fingerprint to identify your PC. And now we can see a few lines below. It also acts as a few other leaves. And I think those 3 leaves contain the model name of your CPU. So if you have an Intel i7 CPU, then that's the string it's stored in there. And Denuvo accesses that and uses it as an identifier. We can see also an access to K-user shared data. And for those of you who don't know what that is, that's a special memory region that each Windows process has. And it contains data that processes might need, but they need it without a big overhead. So for example, if you want to measure the time between 2 functions, then you can access the system time through this K-user shared data memory region. So it contains system time, processor count, memory size, how much RAM you have. So it contains all sorts of data that needs to be accessed frequently. And specifically, Denuvo at this point accesses this time zone bias, which probably contains the time zone you're in. But I think this is not part of the fingerprint. At least I tried to patch that and it didn't change anything. So I assume they use this to seed some random number generator or something. So this might not be relevant as an identification feature. A bit down below, we can see like this whole chunk essentially belongs together. We can see that it accesses the process environment block and then it accesses NTDLL. But we'll skip over that for now. I'll come back to that later. Here, we can see that Denuvo accesses K-user shared data again. And it reads, for example, the product type you have. So for example, if you're Windows Professional or Enterprise or something like that. It also reads the amount of physical pages you have, so essentially the amount of RAM that your PC has. And it also accesses the active processor count and the build version. So all these fields and memory accesses are part of the fingerprint that Denuvo generates. And down below, we can see the first interesting API call that happens, which is called expand environment strings. And that's an API provided by Windows to essentially expand environment variables. And we can see that Denuvo tries to fetch your computer name using this API call. So this is definitely also part of this hardware ID fingerprint that Denuvo collects. Then some more time zone stuff, so I assume this is RNG again. Then it executes the CPU ID instruction again. So we can see that Denuvo performs the same actions multiple times. So it might execute CPU ID multiple times, even though it already got that information. And down below, we can now see again that Denuvo is reading from NTDLL. And what's happening there, or rather in this whole block, is I think Denuvo is not performing an integrity check, because I think there is already research on Denuvo, and there were people who said that Denuvo is doing an integrity check on NTDLL and essentially verifying which Windows version you have by doing that. But I think that's not what happens, because if we scroll down to this line, we can see that Denuvo executes a syscall instruction to query information about your system. And it obviously uses that as part of your fingerprint, because this returns information that could be helpful to identify your PC. But the important thing is that to be able to issue a syscall instruction, you need the syscall ID. And the syscall ID can be obtained by crawling all the exports from NTDLL and then disassembling all the functions until you find the one with the right syscall ID. And I think this is what happens here. So Denuvo is accessing NTDLL and reading all the function names and trying to find the one that matches the syscall, and then it's disassembling all the code to find the matching syscall ID to be able to perform this inline syscall. Denuvo also executes a RDTSC instruction. I don't know what that's used for, and again, I assume they probably seed some internal RNG using that, but I might be wrong. Same goes for this RNG seed version. I think this is not used to identify your PC, but it's rather used to seed some RNG, which makes sense. Yeah, again, query system information syscall, so we see it's doing the same thing multiple times, and we'll later see why it does that. But right here, we can see that it accesses the process environment block. If you don't know what that is, that's a block of memory that every Windows process has, and it contains information about this process. So it contains the environment variables, it contains the command line, and it also contains process ID and everything that's relevant and unique to this process. And by doing that, Denuvo accesses environment variables directly. But I think in this case, this is also not for the fingerprint, because I tried to patch that and it didn't change anything. So I think this is something that's either seeding an RNG, or Denuvo has something that I think it's called execution paths. And the idea behind that is that, for example, you have a function in Hogwarts Legacy that's responsible for casting a spell. And I think what Denuvo does, it takes this code of that function and it duplicates it a few times. For example, there are three variants of this function, which all do the same thing. They cast a spell. But Denuvo protects them differently, and it can then at runtime decide which one of them to execute. So it has different execution paths. And by doing that, as a cracker, you have to find all these execution paths and patch all of them. And I think the access to those environment variables here is used as some kind of selection mechanism for those execution paths. So depending on how your environment variables are set up for the process, it decides to execute a different code path. So not part of your fingerprint, I think, but code path selection. Down below, it also accesses the PEB and tries to get version information about Windows. And this is definitely used to identify you. It also accesses the number of processors, so similar to what's stored in K-user shared data, they have quite a big redundancy within the data they use. Again, here CPU ID. And here we can see another API call, get keyboard layout. And I think, again, this one is not relevant for the fingerprint, but rather is used for this code path selection stuff. So I did not patch that at the end. Again, trying to read the computer name using this expand environment string. It also accesses your system time, and I'm pretty sure that is part of this RNG seeding process, so we can safely ignore that. Here it reads 4 imports again. So it accesses the import table again and reads 4 functions from ADV, API, and kernel32 DLL. And those are definitely relevant. So they're using the addresses stored in the import table to identify your PC. We can also see an API call, get username, which obviously returns your username. And all this gray stuff is uninteresting. It fetches your Windows directory, so where your Windows installation is located on your drive. It also reads information about your C drive. I don't know exactly what this returns, but information about your hard drive. It again fetches the computer name using a different API. So it has your computer name multiple times, probably uses that to to verify that you did not patch anything. And at the end, we can see an API call called crypt acquire context. And this essentially accesses Windows crypto library. So this is the crypto API that Windows provides. And I think you can use that as a fingerprint feature. And the way it works is probably that you can call this API and tell it to encrypt some chunk of data. And the key that's used to encrypt this chunk of data is some key that's specific to your PC. And by issuing this API call, Denuvo can get data that is encrypted in a manner that is unique to your PC and essentially use that as a fingerprint feature. And I think that's it. Because down below we can see that it starts loading the Steam API DLL. And I obviously don't have Steam inside this Windows environment in the browser, so this will obviously fail. And can you still hear me? Okay, good. And then at the end we will see it's still trying to load the Steam API. And we can see a message box at the end that it's not able to load the Steam API DLL. And then it just dies. But we don't care because we got everything that we're interested in. However, at the end, the emulator prints us an instruction summary. So what this is the emulator counts the CPU ID, the CPU instructions that were executed and lists them in ascending order. And we can, for example, see the syscall instruction that it executed, but we can also see, for example, an xgetBV instruction. This one behaves similar to CPU ID, so it essentially, I think, returns capabilities about your CPU. So Denuvo also uses that as an identifier. And I think other Denuvo versions also make use of special instructions that behave differently on different CPUs. There exist instructions that, for example, if you execute them on an AMD CPU, that behaves in a slightly different way than if you execute it on an Intel CPU. Or, for example, if you execute it on an old Intel CPU, it behaves differently. So there is a bunch of instructions that behave in that way. And Denuvo definitely uses them in newer versions, but I think Hogwarts Legacy doesn't make use of any of them. In general, if it does, they should be among the first 10 to 15 instructions, but I don't think there are any special instructions in there with that behavior, but I might be wrong. And that's about it. So I know that that was a lot of input, but you don't have to remember everything. But the emulator essentially helped us to analyze what the Denuvo binary does and how it identifies your PC. And now that we know the identifiers that Denuvo uses, we can try to patch them and to replay these identifiers from a different PC. And this is what we can do now. We'll try to patch Denuvo, but the way I did it is just a proof of concept. So I was not interested in cracking the game. I don't have the time for that. So I try to more or less create a proof of concept to run the game on my PC. And the way I patched API calls in general, so for example, this get username or get Windows directory, the way I patched them was by just hooking them, because it seems that Denuvo does not have any kind of integrity check on those API calls. So the way it works, you see that Denuvo calls, for example, get username A. And what I did is I created a fake get username A that returns the name of my other PC. And I essentially inserted a jump instruction on the original. So it always redirects to this fake one. And then that's fine because Denuvo does not verify that. And that way we can essentially bypass all API calls, at least in this Hogwarts Legacy version. The next thing is import integrity. And patching that was also relatively easy. I did that by allocating a trampoline at a fixed memory location, and then I jump to the original import. So you have the game import table, which essentially is a list of all functions from libraries. And what I did was I allocated a chunk of memory at this exact address, and it's always this address. And I just write this address into the game import table. And here I just also create a jump instruction that forwards to get username A. So when Denuvo reads the import table, it always sees this address, no matter which version of this DLL is installed on your PC. It will always be this address, and for the next import, it will then be the next address in there. So all imports in the game will always have the same address, and that way the feature that Denuvo collects will also always match. The next identifier is all the entries in the process environment block. To patch that, also took the easy route. I essentially unprotected the memory and overwrote all the data with constant values. So for example, if you the OS version that's stored in there, I just wrote the OS version of my PC. And this can definitely have undesired side effects. So for example, if a library within the process reads this Windows version to determine if it supports some special API or not, then your PC can obviously crash if you don't have the right version in there. But I didn't really care. It was just a proof of concept. So I overwrote everything I could. And that way I was able to patch the process environment block. Patching K-user shared data was pretty hard. And this is where it starts getting super technical. So don't mind if it gets really technical. But the way I did that is overwriting memory, like for the previous one, did not work. I think that's because the kernel prevents that. And what I did instead, I tried to find every location in the game that accesses this memory region. So I attached a debugger and I did some sampling and I played the game, and essentially I tried to collect every memory access, every instruction that accesses K-user shared data. And this is obviously pretty trash. So I will definitely miss places, and with this path selection thing that Denuvo does, I will definitely not have explored all the code paths that there exist. But again, I didn't care. It's just a proof of concept. And using this sampled data at runtime, I then create a hook by disassembling the original instruction, and then I create a fake K-user shared data, and I redirect this memory access there. So it's a pretty bad approach, but for my proof of concept, it works. For the CPU ID instruction, I was way too lazy to redo what I did for K-user shared data, and I made use of a hypervisor. Maybe some of you are familiar with that. A hypervisor is mostly a driver or a standalone piece of software that is used to virtualize operating systems. So that's the core part of software that is used to run virtual machines on your PC. So for example, if you want to run Linux on Windows or the other way around, there is a hypervisor that manages all that. And the way virtual machines work, the way they are so fast, is because most instructions run on your real CPU, except for a few special instructions that should not be executed on your real CPU. There is a way for the hypervisor to intercept those. And this works by registering a callback at the CPU. And if one of those instructions is executed, the hypervisor is notified and then can deal with it, for example, by returning the values that it needs to. And you don't need to run VMs using a hypervisor. You can just make use of the fact that you can register this callback at the CPU. And this is exactly what I did. So I just register this callback, which is called a VM exit handler. And by doing that, I'm able to intercept any time the CPU executes a CPU ID instruction. So if your game runs and it executes a CPU ID instruction, my hypervisor driver is being notified that the game does that. And then I can check where does this instruction come from. So I check if it's Hogwarts Legacy, and then I just patch the values that it returns. And by doing that, I can also patch this xgetBV instruction by disabling the feature bit in CPU ID that tells Denuvo that my CPU has that. And I then essentially mimic the other PC. Doing that is technically really dangerous because you tell the game that it has CPU capabilities that it really does not have. And this can definitely have undesired consequences if you run it. But again, I didn't care. It was just a proof of concept. I just wanted to get the game run without owning it, so I didn't care. For the inline sys calls, I was not able to patch them because it turns out that Denuvo has some mini integrity checks on them. So you can't just patch the memory where those instructions are. They need to stay intact. That means we're unable to hook them. And at this point, I just made use of the hypervisor again. And it turns out that a hypervisor can hook CPU ID instructions directly. But my hypervisor wasn't able to do that at that time. So I made use of something that's called EPT hooking. Unfortunately, I don't have the time to explain in detail what that is. So if you want to know more about EPT hooking, you can follow this link. But in short, it allows to modify code in a way that the user mode process is not able to see. So you modify the code bytes, and the user mode process still thinks that the memory is completely intact when reading it, but when executing it, it executes the patched one. So the hypervisor allows to do that, and by that I can patch the syscall instructions. There might be other features related to this fingerprinting. For example, the NTDLL reads that we saw. At the time when I was developing my bypass, I didn't know that these NTDLL reads were no integrity check. So I still try to patch them by inserting some fake NTDLL into the map module list. But it turns out that it didn't matter, so it didn't change anything. And as I mentioned previously, Denuvo uses undefined instruction behavior, so it makes use of instructions that behave differently on different CPUs. But it seems like none are present in Hogwarts Legacy. I was able to see some in later versions, but in the version I analyzed, I was not able to find some. Doesn't mean that I didn't miss them, but yeah. Using that, I was able to get Hogwarts Legacy running after 5 months of work. So, could have spent my time a bit better. Thank you, thank you. So if you want to do the same, I cannot recommend it unless you have 5 months of spare time. But I was really happy to get everything to work, and here's a screenshot of when I got it running. So the thing is, again, did I manage to fully crack the game? And the answer is obviously no, I did not. I just cheated in a lot of places. But the thing is, what does that leave us with? The game, in the end, I got it to run, but it's super unstable. And the reason I think this is the case is because sampling those k-user shared data memory accesses is trash, so I probably missed values, and patching the CPU ID and process environment block definitely destabilizes the system. And the way I patched everything else is also probably garbage, and I might have overlooked something. But in the end, I still had about 2,000 hooks, so I patched the game at about 2,000 locations. And at that point, I thought to myself, I can surely do something with that. So I hope that those 5 months were not wasted. And so what I did, I tried to do some performance reasoning about Denuvo. So I used those hooks to reason about how the Denuvo affects the performance of the game. And we have to be careful here. This is not a performance measurement. I cannot do a measurement because I don't have a version of the game that is not protected by Denuvo. So I try to reason on the behavior based on the hooks that I installed in the game. And what's important to note is that Denuvo vastly changes for each game. So the analysis that I'm doing here might not necessarily apply to older versions of Denuvo, and it also might not necessarily apply to newer versions of Denuvo. And if you see some performance analysis on the internet, that's the same. So it might be true for newer versions, but it also might not be, because Denuvo changes so much on each game. But what I did is I used those 2,000 hooks, and I tried to print a line called Momo overhead. So inside my hooks, inside the code, I inserted a print statement which prints this text. And by playing the game, if we don't see a line being printed, that means that none of this Denuvo verification code that uses my hooks runs. And that also means that no performance impact was possible during this moment. And if we see a print, that means that there is Denuvo code running, because I had to patch it. And that means that there is a possibility for a performance impact. So there is a chance that your FPS are dropping, but we don't know. We don't know how big the impact is. We just know there is one at this specific moment in time. And now we can see a video, but I'm not playing it via YouTube. So what we can see here is the game running, and here's the console that should print Momo overhead. And if I press play, we can see that there was a new print incoming. If I'm running around, you can see there were 3 prints now. For example, right now there is no print incoming, so there was 1. Right now there is no print coming, so no Denuvo check running. There was 1 right now. And most of the time there is no check running. So you can see I'm running around and Denuvo is not doing anything. But the moment I am running through this door here, there will be a transition sequence, and we can see there is a huge chunk of prints. So there were 6, 7, 8 Denuvo checks executed during this transition moment. And the clip is unfortunately really short. The reason is that the game crashed about every 20 seconds. But we can still use that to reason about the performance impact that Denuvo might have. Because what we saw was there were a few prints while running in the game. So a few prints means that there was very few interaction from Denuvo during this time, and that in turn means that frame drops are unlikely. Doesn't mean that there were none, but the chances of there being a frame drop is pretty much 0. There were many prints during this transition sequence. So when we went through that door, we saw there were 7 or 8 prints, and that means that a huge chunk of Denuvo checks were being executed, and in turn that means that there is a chance of FPS drops occurring. But again, you don't really care because this was a transition sequence, there was this loading sequence, and you don't care about FPS drops in such moments. And what we can definitely see is that Denuvo is not constantly hammering your system, so there is not 1,000 checks running every second. There is maybe 1 every few seconds. So there is definitely no big performance impact possible. And what we were able to see during this video, that the most of the checks were running during this transition sequence. So that means that if you play the game, the chances are that if there is a performance impact, it's probably at times where you don't really care that it's happening. Of course, this is no absolute proof. This is no accurate measurement. I was only trying to reason about the performance, but it can still give you a bit of a feeling of how Denuvo performs and how it affects your gameplay. So I personally would say that Denuvo likely does not impact the gameplay of Hogwarts Legacy, so you can play your games and don't have to worry about the performance impact. Hold on, there is still a summary. So to sum it up, patching Denuvo required thousands of hooks, and the integration is different for each game. This is, in my opinion, the key point and what makes Denuvo so strong. So if you try to tackle a new game, you essentially have to start from scratch. You can't reuse much. And finding those fingerprint features, so developing this emulator, it costs me a huge amount of time. And doing that is, in my opinion, conceptually hard. You need to think about how it works. You need to know about the internals of how Windows works. So doing that is a hard task on a conceptual level. But patching those fingerprints is essentially easy. Like you patch the memory, you create a hook, and then you redirect it and return a fake value. Doing that is pretty simple compared to finding the fingerprint features. But the issue is that there are thousands of places, and finding them is pretty much impossible with all those different code paths and the randomness the game has. So you somehow need to explore 100% of the game code, which is pretty much impossible and would take a huge amount of time. And I don't think there is a real incentive to spend this amount of time, but because you're not getting paid for cracking the game, because the people who could pay you could then also just buy the game. So they don't have the money to pay you. So there is not really an incentive to spend 5 months on cracking Denuvo. So as a researcher, you're essentially happy that you found the fingerprints, at least I was, and I didn't really care about patching all of them. But you would have to if you wanted to create a crack. And in my opinion, this is what makes Denuvo so strong. So they make the easy challenge look hard, but the hard challenge look easy. And there is a bit of an outlook. In the past months, I managed to probably reliably bypass Denuvo in black with Wukong, but unfortunately, I can't share any details, and I also won't release any cracks, so don't ask me for a crack, please. That's it. Thank you.
A ver, ¿preguntas? Sí, por allí. Vale, ok. En inglés, ¿qué traducción simultánea de momento para las preguntas? No.
Hi, thank you for the talk. I wanted to ask you a couple of questions. So
Okay, sorry.
the first question is if you have been contacted by Denuvo to,
Yes, I have.
to discuss. You can answer this question later. And the other question was like, so I know you focus on the hardware ID identification, and it's good. My question was if your framework or if you came across any anti-emulation. I know you were implementing the inline syscall, to be able to continue the emulation. But did you find any anti-emulation, like timing checks or like exceptions or interruptions or dirty tricks to detect unicorn?
So, to answer your first question, yes, I was contacted by Denuvo when I visited them, and they are super great guys. And I also have permission for this talk, so you don't have to worry that I'm getting sued. But to answer your second question, I don't think that I have seen anti-emulation stuff running in Denuvo, but that doesn't mean there is none. So what I know for sure is that they're using these undefined instruction behavior. So this essentially is some kind of anti-emulation technique in a sense, because probably Unicorn has a lot of bugs, and chances are high that Denuvo is abusing them. I don't think that this Hogwarts legacy version has any of those anti-emulation features, but I'm pretty sure that later versions definitely do have something like this. There was an environment variable called anti-tamper timing something by Denuvo, so they definitely have some timing stuff in there, but I don't know how it works, and I didn't have the need to analyze that. Any other questions?
Okay.
Holy
Another.
Hello, thank you for your incredible talk. I wanted to ask you if you have, well, there have been plenty of crackers in the past that have targeted Denuvo and managing to break it successfully. Have you performed any analysis of these Denuvo free versions as compared to their normal builds? Thank you.
You mean having compared a Denuvo free version of a crack to a normal game? I did not look at any other. I shortly looked at the Empress crack of Hogwarts Legacy, but she made it for a different game version, so I was not able to reuse anything she did. So, no, I did not look at any other cracks.
Another one?
Hi, thank you. I've got 3-ish questions, if that's okay.
Okay, go for it.
How do you, I mean, it's gonna be pretty insane, the way you, how do you know if, there's so many different data points that you're looking at, and how do you have any kind of feedback from the processes? Like, from the beginning, you got into the binary straight on, like you didn't go through Steam, so that's already a decision. How can you tell which variables, which data points are actually, involved into the final token and which aren't?
This is actually an amazing question because this is super difficult to figure out. And the way I did it is if the token, or essentially if a feature does not match the token, Denuvo creates some kind of message box with an error code. And if you modify some data and you see this message box, then you know you have invalidated the token. Mm-hmm. But what you do not know is that you have found all the data points, all the features. And that's why I spent like 5 months, and the last 3 months I spent on finding the single last fucking feature, sorry. And it was super exhausting. And yeah, so this is actually the thing that makes Denuvo strong, because you don't have much feedback. And this is intentional. They don't give you much feedback, and you have to stay in the dark until you have found everything.
Right. You've probably already answered this with her question, but as far as I know, like the only people capable of, fucking with Denuvo are like Empress, Fit Girl, and not many more people. So, and there's also been talks of Fit Girl trying to teach some other people how to crack Denuvo and not being able to. Do you think that's a skill issue? It's just a matter of, lack of incentives, or what's the deal with that?
So from what I know, I think Fit Girl doesn't do any cracks. I think she only repacks, but I might be wrong. But I think one of the core issues is that to be able to spend 5 months on something, you kind of need to be autistic. So,
yeah,
I mean,
aren't we all?
Who would spend 5 months on that? And I don't know why I did that. I don't know. And to be able to teach that to others is, you're also putting yourself at risk because you can get sued, and you have to be very careful. I think Empress can do that because she lives in Russia and nobody cares about that, but teaching others while having, let's say, issues with communication is maybe a bit hard, and then also teaching them and endangering yourself. And also, being able to crack the Denuvo game is something like, it gives you a lot of prestige, let's say that way, and teaching others would be like giving your trophy away in a sense, you know what I mean? So maybe that's 100%. The reason others don't do it.
Nice. And the last one, stepping a little bit aside of the technical side, as a modder yourself, how do you see the situation with paid mods? How do you think we can go forward, and how do you see, for example, what Bethesda is doing? Should they get a cut? The game is theirs. Should they get a cut for the modders' work? Paid mods, yes, no. How do we go forward with this?
So you mean if modders should get a cut of the earnings from the game?
No, the company. Should the company be in between like Bethesda does? Well, Bethesda has their own like Bethesda workshop thing, and they get a cut from the modders' work. How do you see that? I mean, at the end of the day, it's their game, but
I mean, as a modder, you're always in the wrong. It's always a gray zone to be a modder because you don't own the intellectual property. So the company can do anything. I think morally, they should not get a cut, but they can, so why shouldn't they? But I don't have any strong opinion on that, so.
Fair enough, thank you.
Can't say much.
Another one? There. Okay. Let's go. Last one. Follow the leader, follow the leader. Sígueme. Pero se hace risa.
Hi, thank you for your talk. It was amazing. I had a lot of fun. It's a much simpler question. I'm just curious about, are you working on Borderlands 4? And if you are, based on your findings, would you say it does affect performance or not?
So I took a look at Borderlands 4, and what I can say is that letting the startup sequence of Borderlands 4, so the Denuvo startup sequence of Borderlands 4, run in my emulator takes a huge amount of time. So it takes 30 minutes, and you were able to see the startup sequence of Hogwarts Legacy. It was maybe a minute, maybe 2 minutes, but definitely not 30 minutes. So Denuvo has definitely changed But I contacted the Denuvo devs, and they told me that this is likely intentional. I mean, they obviously can't tell me something, but chances are low that Denuvo causes these performance issues in Borderlands 4. So this is probably some Unreal Engine stuff going on. But I still noticed changes in Denuvo. But I don't know anything for sure, so I can't say if they really do or do not cause performance issues in Borderlands 4.
Muy bien, pues otro fuerte aplauso para Maurice.
Thank you.